Okay, based on what we have discussed last Tuesday, we ended with the conversion of A, and that particular conversion is already on the second reactor. And by the way, what is our second reactor? That would be the what?
The PFR, miss.
Okay, so that's the PFR because we connected our PFR to our mixing tank, which actually functioned as a CSTR or a back mix reactor. So based on the calculations that we did last Tuesday, what is the value of XA2? Have you computed for XA2 based on the integral that was asked for you to be processed? So our XA2 last Tuesday is point. Can you just have it type written in? Thank you.
Point
Sige. Okay, mas ano siya,
704.
0.4. Okay, thank you. So we have 0.704. So this is the conversion. This is the conversion of A in the PFR. So XA2 is the conversion of A in the PFR. As to the question given in the problem, let me read it again. It says, what is the concentration of R at the exit of the PFR and the conversion of A in the system? So meaning, what would be the conversion of A now considering the two reactors? So how would you determine the overall conversion of A in your system? So in the system of the MFR and the PFR. In that case, you need to solve for the final concentration of A as it leaves your PFR. So let me go back to the Jamboard. So you need to determine CA2. The concentration of A as it leaves your PFR, and that would be your CA1, its concentration as it enters the PFR, 1 minus XA2. That would give you CA2, the remaining concentration of A. Were we able to determine the CA1? Okay.
0.008.
Okay, your CA1 is 0.008. So this is the concentration of A as it entered the PFR. So we have to multiply it to 1 minus 0.704. So your CA2, the concentration of A leaving the PFR would be okay. So Nika wrote here 0.002368. Our set units here is mole per liter. And by the way, we changed already our volume units in cubic feet for our reactors to liters. That way we won't have any conversion anymore. So this is our CA2. So our overall conversion, CA, so that's overall conversion would be just the same as how we determine conversion for, let's say we're just talking of one reactor. So that would be the initial concentration based on our formula, initial concentration 1 minus XA, where XA is our overall conversion, should be, so let me just change this so we can, CA2. The XA here that we are now solving would be the overall conversion. So you will have CA2, which is 0.002368. Your CaO, how much is our CaO? 0.01. You have 1 minus XA. Kindly correct me if I'm wrong. So you have now XA, which is the overall conversion for the system of reactors. Okay, can you solve for X8, please? .7632. Thank you, Nika. So our overall conversion in this sense. Wait, do you see the Jamboard? 0.7. Okay, 632. Okay, so this is overall conversion for the system. So this is this is one answer that we need to take note of for the required. Next would be the CR. So specifically, the question here is, what is the concentration of R at the exit of the PFR? So since we have CR1 from the mixed flow reactor, then we will label the concentration of R at the exit of the PFR as CR2. Okay, so we'll have CR2. And that would be CR1, 1 plus XR2. Now, this could be translated to CR1 plus CR1 XR2. And what is our CR1? This is our CR2. Let's say this is our first equation here. What is our CR1? Remember, there is some R formed already in the MFR. So and there is no initial concentration for R. So our CR1 would be 0.002. That's correct. So this would be 0.002. As for this one, we can have this like CA1 XA2 based on stoichiometry over 1 is equal to CR1 XR2 over 1 as well. So we have here our CA1. Our CA1 is 0.008. And our XA2 is 0.704. And this would be your CR1 XR2. So that would be how much? CR1 XR2 is equal to 0.005632. So that should be added to this point. Okay, I will just erase so it will not be crowded here. So I'll just place here CR2, then would be 0.002 plus 0.005632. So CR2 then would be 0.007.007.632. So this is mole per liter. Okay, so this is the concentration of R that leaves your PFR. So it will include the R that was partly already a product of the reaction in the mixed flow reactor and the R that was formed in the PFR itself. Okay? So this is our solution. We went back to this conversion that we got last meeting. We determined the final concentration of A as it leaves the PFR. we use this final concentration together with the initial concentration of A as it entered the first reactor in our system, which is the MFR, to get the overall conversion. Because this 0.704 is the conversion in the PFR only. This is not the overall conversion. So the overall conversion is always based on the final concentration, or that is the unreacted part of the reactant, and the initial concentration of that same reactant. And that's how you account for the overall conversion for your system of reactors, meaning if you have several reactors already in your system. And finding the final concentration of R would, of course, need this fundamental equation, since R is a product. So that would be the initial concentration of R that is processed in the PFR multiplied to 1 plus. So it would be plus XR2, the conversion of R in the PFR. So your amount of R produced in the PFR based on stoichiometry can be based on the amount of A consumed in the PFR as well. So the amount of A consumed in the PFR is its initial concentration times its conversion in that same reactor. So based on our values taken previously, so we have this one, and we just need to add the two. Any question here before we proceed with the remaining part of the slide? Okay, so I think there's no more questions. So I'll go back to our slide now. Okay, so that's our second problem. Then we go to the next. So at present, the elementary liquid phase reaction, A plus B forming 2 moles of R and S, takes place in a PFR using equimolar quantities of A and B. Conversion is 96%, and the initial concentrations of A and B are 1 mole per liter. Now, if you're going to connect a backmix reactor 10 times as large as the plug flow reactor in parallel to our original unit, which is our MFR, PFR rather, that's the PFR, by what fraction would production be increased? So how will the amount of processed reacting system increase? Letter B, does the concentration level of the feed affect the answer in A? So meaning, will the concentration of the feed to the PFR, both in the PFR and the backmix reactor now hooked in parallel together, affect your answer in A? And if so, in what way? Now, you have to note, there's a note here that conversion is to remain unchanged, whether you just have one reactor, that's the PFR, or you have both reactors already operating. So conversion is to remain unchanged in that case. Okay, so now we go to the Jamboard. But before that, you may take a screenshot of the problem. That way, you will have ease in following the supply of information, or you can aid in the supply of information when we write down our solution. Okay, so now I'll go to the Jamboard. So this is our third sample problem here. And of course, we need to write first what is given. So originally, you have a PFR. And then you're going to hook up to this one a CSTR. So it says in the problem that conversion is 96%. So meaning whether this is only the reactor that is working, your PFR alone, or both, the conversion in both streams when they're hooked in parallel should be the same. So here we'll write CA here is equal to, so we'll just leave it for now, but we know, I'll just here CAP, meaning that's for the plug flow, and this is CAM for the mixed flow reactor. So in both cases, you will have 96% conversion, whether PFR is standalone or it's hooked in parallel with the MFR. Okay. Now, your initial concentration for A and B, they should be equal. Wait, guys, I'll just write it here. And the concentration is 1 mole per liter. Okay. Now, we have a corresponding volumetric flow rate here for the PFR. And we have the corresponding volumetric flow rate here for the MFR. Okay. Now, our reaction, we'll write our reaction here. It's A plus B forming 2 moles of R and 1 mole of S. This is an elementary liquid phase reaction. So we'll right away write epsilon A is equal to 0 because of the phrase liquid phase reaction. Okay. So if a back mix reactor 10 times as large as the plug flow, so if the volume of the plug flow is capital V sub P, the volume of the mixed flow reactor is 10 times that of the plug flow reactor. So make sure that you write your volumes as capital V and your volumetric flow rates as small letter V, so there won't be any confusion later on when you get to review your notes. Now, a while ago, I placed here the final concentrations of A as it leaves both reactors, plug flow, and MFR. If both will be having the same conversion of 96%, and initially both will have to process a stream with initial concentrations of A and B equal to 1 mole per liter, what do you think will be the concentrations or the amounts of A leaving these two reactors which remained unreacted? Or that, shall we say, the final concentration of A in both reactors using the conversion which is given to be 96%. What do you think would be CA or C sub AP and C sub AM in this case? Okay, you can write your answer on the chat box. What do you think will be the final concentration of A in the plug flow reactor based on this conversion? And what would be the final concentration of A in the mixed flow reactor based on this same conversion? Because as stated in the problem, conversion is to remain unchanged, even if we have to hook up a back mix reactor 10 times the size of the plug flow reactor to the original plug flow reactor. What do you think will be the final concentration? Okay, correct, Bobby. That should be 0.04. So initial concentration times 1 minus X. So this is your conversion. So then it follows that for both of this, your final concentration would be at 0.04. So very good, Bob. So this will be your concentrations of A leaving the two reactors. Okay? Now we proceed on the next slide to continue. Now, can you provide me, so your required information, so we'll write it here, it's crowded already there. So letter A, how much will production be increased in the new setup? Okay. And letter B, So this is, you need to explain here, but when you explain, of course, there has to be support, mathematical support or validation. Does the concentration level affect or will CaO or CbO, aura, that's not division, affect? Answer in letter A. In what way? If your answer is yes, in what way? Okay, so that's our required, the two required information. Okay, now since our system starts with, or a problem rather, the original statement in the problem that we only have a PFR given, then we start with the PFR. So we need to write the performance equation for the PFR. What's our performance equation for the PFR in terms of, let's say, in terms of concentration? Can somebody give the performance equation for a PFR in terms of concentration?
Tau is equals to C, to the integral of dCA over RA,
Okay.
evaluated to CaO to Ca.
Okay, thank you. So CaO to Ca. So this is for the PFR. Okay, for the PFR. Now, this tau we can change to, based on our representation, the volume of the PFR divided by its volumetric flow rate. So I will have this just subscript P, so meaning is for the PFR. And then we'll have here CaO, Ca. And we will have dCA. This time we need to specify our rate law. So our rate law will be, in this case, it says in the problem that we're given an elementary reaction. And this is our stoichiometric equation, an aqueous elementary reaction. And we're starting with equimolar amounts of the species that needs to be reacted. So what would be the corresponding rate law in this sense, the appropriate rate law? What should I write here? Okay, so you'll have, okay, C sub A, C sub B. But we will have a problem with the C sub B because our unknown function here for our integral is C sub A. So we need to change C sub B in terms of C sub A. We have learned this in midterm that whenever we have equimolar amounts of the species, of the two species that are to be reacted, and if the reaction is elementary, this particular rate law can even be simplified in the form. So by the way, I'll place this one as 0.1 already. So I will have here Ca2 this is 0.04, and we'll have here dCA. I'll have here K, and I'll write this as Ca squared. Okay, I hope you recall what we did here. We changed the Cb to CbO, 1 minus xb. Your CbO is equal to CaO, and your CbO(xb) is equal to CaO(xa). So it follows your C sub B is just your C sub A. So we have done that already in midterm. So this will be now the appropriate. Yes.
Ang basta imbis nag-equate lang si C sub B kay tungod equimolar sila.
Amo na
Hindi
siya.
kay
So that is the reason why we did that last term. Like CB is equal to CBO, 1 minus XB. So this would be CBO minus CBO XB. Your CBO is CAO, and your CBO XB is CAO XA as well, based on stoichiometry. So therefore, C sub B is C sub A. Okay, we had done that. We have an exercise on that when we were deriving a particular expression. So we change it to this, and we substitute the things that we need to substitute. So we're not given the volume of the plug flow, nor are we given the volumetric flow rate. So, but we can have here the substitution to the integral. So I'll have here V over small v for the plug flow is equal to, I'll just place the K outside the integral answer. So your answer would be, in this case, you have CA squared. So this would be CA raised to -1 over -1. So that would be negative. So I'll place the negative here, and I will have 1 over CA minus 1 over CAO. And you will have -1 over K times 1 over 1 minus 1. Oh, sorry. Your CA is 0.04. Wait, huh? Okay, so that's it. 0.04 because you started with 1. I'll place here 0.1. So this is 1. Okay, please check your copies. So the right side, if we will simplify the right side, what's our answer? V over small v. P is equal to, what's the equivalent answer for the right side, please? Is it negative? Or is it positive already? 1 over CA, final concentration minus the initial. So negative. Is my integration correct? This would be CA raised to -1 over -1. Oh, so this should be negative DCA. I think, Bobby, this is negative DCA over the rate. So this makes it positive already. Because this concentration is expected to be decreasing. So we cannot have a tau which is negative. So there should be a negative sign here. Because this DCA will be a decrease in the concentration over time. So you will have a negative here. You'll have a negative here. So the answer will be 24 over K. Positive this time. We'll just get this one. Positive na siya. So this will be 24 over K. So this is our first equation. We haven't yet written any equation. So this is equation 1. And we do the same for our back mix reactor. So for our MFR, what is our performance equation for the MFR? We have V over small v. That would be, for the MFR, that would be its tau equal to CAO XA over the rate. Okay? CAO XA over the rate. Now we know that this volume of the mixed flow reactor is 10 times of the volume of the plug flow reactor. So this time I will write now this as V sub M. And this is equal to, so you have CAO is 1 and XA is 0.96. And we will have here, as written a while ago, this is K, CA squared. So CA squared. So the remaining amount of A in the mixed flow reactor is 0.04. So 0.04 squared, right? So we have now, can we simplify this part first? How much is the answer here? We have 600K. 600 over K. Sige. So we'll have 600 over K. So this is our equation 2. Now, if you look very closely, your equation 2 has a right side in terms of K, and equation 1 has also a right side in terms of K. You can equate K's if you want, but the simplest thing to do here is to divide the two equations. That way you get to cancel the K. So if we divide 1 and 2, so we'll copy our 1. So so capital V, P over small v, P equal to 24 over K. We divide it by, if I'll take out this 10 here, this will make it 60. So I will have capital VP again, but this time it's VM equal to 60 over K. So in the process, you get to cancel the capital VPs, the volume, and the rate constants. Okay? So then, after cancellation, you will have an expression leaving you with VP as a function of VM. So VP is equal to, can you solve 24 over 60? Or this would be VM. 24 over 60. 0.4. Let's check. Okay, so 0.4. So this is 0.4. VM goes up, VP remains here in the denominator. So the volumetric flow rate that is being processed by your mixed flow reactor is 40% of that of the plug flow reactor. How does this translate to? So meaning in the new scheme, the total volumetric flow rate will be the volumetric flow rate of the plug flow reactor, originally standalone, operating standalone, and that of the mixed flow reactor now hooked to it in the system. So this is VP plus 0.4 VP. So it's 1.4 VP. The new volumetric flow rate being processed by the system now in comparison to your PFR working alone is 40% higher than the original. So therefore, we say production is increased by 40%. So this is our answer for the first question. How much is production increased if a back mix reactor 10 times as large as the plug flow reactor is hooked with it in parallel scenario? So this is the percentage increase in the production. Do you get it? As for the second question, the second question is asking, will the concentration will the concentration of A and B affect the answer in letter A? So meaning, will this 40% increase in production be affected if we're starting with a different initial concentration, either higher or lower than 1 mole per liter? What do you think would be the answer? Will our answer be affected if the initial concentrations of A and B will be different? You can write your answer on the chat box. Will our answer be affected if we started with different initial concentrations?
Malainay miss ang ratio ni CEO ug CBO amo.
Malainay. No, I wrote it differently. Wait ha, it's not division, Bob. It's or. Okay, hindi na siya. Division. Or. Will CAO and CBO affect the answer in A? So no, as long as equimolar. As long as equimolar. Okay. Nika says no. So the answer actually is no, because if you look at the equations that you worked on, this is the first equation that you worked on, right? And this is the second equation that you worked on. When you try to get the ratio of the two, you notice there isn't any more initial concentrations appearing here. What is just left is the conversion. Or better yet, if you want to write the equations per se, so you will see that there is nearly no link. We can write with the, we can start with the, oh my, wait class ha, cannot move anymore a slide because I've reached the maximum. Your working equation, I'll just erase a slide here because I used a continuation of the previous wait class ha. I think this is the one that we used last time. Okay, wait, another one. Now, for letter B, so better yet, para clear and that you have mathematical justification for your reasoning that it won't be affected by the initial concentration, you can write the performance equation. So for your plug flow, you have Vp over V small Vp equal to, based on our integration a while ago, you have 1 over K. And then you have here 1 over Ca minus 1 over CaO. Okay? Now you can simplify it further by writing 1 over K. Then you simplify the Ca, or you rewrite the Ca in the form of CaO. So you have 1 minus Xa, and you have here 1 over CaO. Seeing that you have CaOs here, you can take it out. You can factor it out, place together with the K. And you have here an expression of 1 over 1 minus Xa minus 1. Now, that could be simplified to 1 over K CaO. You have here 1 minus 1 plus Xa over 1 minus Xa. Okay, I multiplied already this one by 1 minus Xa. You get to cancel this, and this will be your final expression. Volume of plug flow divided by volumetric flow rate in the plug flow will be equated to 1 over K CaO, and you will have Xa over 1 minus Xa. Okay? So this would be your equation 1. This is already equation 3, I think, because we already have 1. I still wrote. So I already wrote 2. So then I will have to use 3 there. Okay, so this is your equation 3. For the MFR, it's more straightforward. Performance equation for the MFR is this. And you have CAOXA over K. And your CAO, your CA squared could be written as CAOXA squared. CAO, rather 1 minus XA squared, right? Now you get to cancel 1 here. Still have 1 remaining. And you have volume over volumetric flow rate equal to, so you'll have here XA in the numerator. You have K CAO 1 minus XA squared. So I'm giving you already a working equation in this sense for the 2 in terms of conversion. If you divide 3 and 4, you'll have an expression that is freed. Will not contain any more. We have that. And what do we have here? We have this. XA1 minus XA. You divide that with volume and another small v here. Mixed flow this time is this one. XA over K CAO 1 minus XA squared. You get to cancel these 2. So you have an expression that is not dependent on initial concentration. So that's how you justify or you validate your reasoning in B that your initial concentrations of A and B will not whatsoever affect your answer in letter A, because actually for letter A, this is the equation that you are working on. The only difference is that we substituted already the values. But if you will substitute values here, you'll end up with the same answer, wherein volume of the mixed flow will be 40% that of the plug flow. Okay, so this is the working equation that will justify. So as to in what way, so it will never affect the answer in letter A. Okay, any question? Okay, so if there's none, I'll go back to the slide again. So this is our third sample problem for this second to the last slide for the semester. Now for number 4, this will be left for you to work out. You will be given a submission link in Canvas as to the solution of this particular problem. This will be done by groups. The groupings that we had in midterm will still be followed for this particular requirement. Okay? So any questions so far with this before we go to the recycle reactor, the last slide? So this is what we have covered so far for reactors in series or parallel or combination of reactors. We call them systems, multiple reactor systems. Okay, there's none. Okay, I'll stop sharing. Okay, I'll go to the okay. Let me share my screen again. So we're now on the design of recycle flow reactors. Or the design of recycle reactors. So of course, from the name of the reactor itself, we know that the stream that is leaving or the converted stream is being recycled back into the feed stream or combined with the feed stream in this case, because we are recycling a portion of the process stream back into the reactor. So this is our recycle reactor. It could be plug flow in this sense, this is plug flow, but it could also be mixed flow. Okay. You have here the initial molar feed rate. This is the volumetric flow rate. It should be small v, VO. This is XAO. We assume that initially our feed here is not converted. Or even if it's converted, the scheme here would still be the same. Okay, this is how we still represent it. If it's initially converted, then your XAO will not be 0. It will have a corresponding value then. Now, FA1, the molar feed rate, the actual molar feed rate to your reactor will then be the sum of FAO and FA3, where FA3 is a portion of the FA2 that remained unreacted here in your reactor. So FA2 is divided into this stream FA3, and you have another one here. Now, nonetheless, your degree of conversion for this stream that leaves this particular reactor is still XA2, and your XA1 will be now this the degree of conversion of the stream that is really processed by your reactor will be now considering XA2 and XAO. If you recall your circuit analysis, you'll do nodal analysis here. So you will have to, in this particular point, okay, let me annotate. In this particular point, this is your summing junction. And let's say, for example, this is B3 and this is VA2, B1, wait, only 2. Oh. So this would be V2. We know that your V1 is equal to VO plus V3. Okay? If you do your summing junction here, your FA1 will be your FAO plus FA3. If you have here it will place here FA4. FA4 plus FA3 is equal to FA2. Base here into, this is, let's say, 1. So this is from 1, these 2. So you do your material balance based on a particular node that you want to do material balance on. As for your reactor itself, the material balance will be your performance equation for it. So anyway, you just have to correctly label the streams that entered and the streams that leave your reactor. So your material balance will be your performance equation for it, for that particular reactor. So in this case, you have your plug flow reactor, and this is the recycle part. So the purpose of the recycle is, of course, we know, to enhance the purity of the final product, or to enhance, in this case, we use the term recovery, increase the recovery of your final product. Okay, so that's your recycle reactor. associated with the recycle reactor is the recycle ratio. Now, based on definition, we speak of the recycle ratio as the volume of the fluid returned to the reactor entrance. Now, what part of the volume of the fluid that leaves your reactor is returned into your reactor entrance? In terms of the volume leaving the system. So, ang kabilugan nga nag-leave sa system, among imo nga divisor. Ang imo nga numerator is that part that was recycled. Now, it could be, this particular recycle ratio could be interpreted or could be associated rather in terms of conversion. XA1 is equal to the recycle ratio divided by its sum with 1 times XAF, where XAF is equal to XA2. Now, this XA1 and XA2 are this one. So, this is XA1. This is your XA1 and this is your XA2. The XAF in that formula is the XA2. So your recycle ratio can be expressed in terms of those two. So you can write here XA1. So you can write XA1 over XA2 equal to R over R plus 1. So you have here the recycle ratio in relation to the conversion ratio, XA1 and XA2, from this particular equation. And now your recycle ratio is being determined or computed based on conversion. Though in the definition, simply put, based on the term recycle, it refers to the volume that is being processed and the volume that is, say, the sum of the volume that is being reprocessed and the original volume that is fed to the system, to your reactor, that is. Now, for any epsilon A, so meaning you can have a constant density system or not, this will be a more generic representation of your recycle reactor if it is a plug flow reactor. So you see the integral sign here. So meaning your recycle reactor, then it will be the recycle reactor that I have shown. Okay, that of a plug flow reactor. So all you have to do is plug in here the rate law and consider that writing the rate law now will be dependent on the epsilon A. So for example, I'll just annotate here so you will have an idea. Since this is for any epsilon A, let's say your N is equal to 1, first order, then the rate would be KCA. When you rewrite the CA here, you have to recall the CA when epsilon is part of it, meaning if epsilon is not equal to 0. So you have to write this expression as K CaO 1 minus XA over 1 plus epsilon A XA. Okay? This time, you're accounting for the actual value of epsilon A if the system is not a constant density system. You won't have any problem if it's constant density because this term is 0. Okay? So, but nonetheless, this is your working equation. That's your working equation for any order of reaction for any epsilon A for a plug flow recycle reactor. Now, this same equation can be simplified if epsilon A is equal to 0 and you're not working on conversion, but rather on concentration. So your concentration, your unknown function here is in terms of concentration. And notice that you have your final concentration here. And your initial concentration is now your lower limit of integration is CaO plus R CaF over R plus 1. So you don't have a lower limit here, which is simply CaO. No, but rather this one. Okay? So this is a formula provided for you. And if there's a need for you to use it directly for your problem, whenever appropriate, then use this one. Okay? Then, you have here one particular formula. If you have a constant density system for first order and second order reactions, okay, pre-derived already. So you can use these equations directly. And this will be, I think, our final last sample problem on the recycle reactor. And this will be also our last sample problem for ECHE 111. Okay, we have here a reaction represented by A forming B, and which is to be conducted in a constantly stirred tank reactor. So this time, since our representation of a, shall I say, of a recycle reactor is that of a plug flow reactor, I have chosen here a CSTR, which has a recycle stream. That way, you won't be lost when you're given a CSTR already to answer. Okay. The reaction is first order with established rate. So this is first order. You see 2Ca. So Ca is raised to 1. The feed is 100 cubic feet per hour. So this is the original volumetric flow rate to your CSTR. With this concentration, 1 pound mole per cubic feet. The product removed contains 50 pound moles per hour of unreacted A. So this is already the molar feed rate that leaves your CSTR. Determine the reactor volume in cubic feet, and B, the recycle rate in cubic feet per hour, or what it's asking actually for the volumetric flow rate of the final stream that is returned in the reactor entrance. So the recycle rate in cubic feet per hour, so you notice it's in volumetric flow rate, if the hold-up time, or that's the residence time, is 15 minutes. Okay, so this is for our recycle reactor. You may take a picture before we go to the Jamboard, where you will have a reference. So this is our sample problem, our last sample problem. Let me go back to the Jamboard so we can write the solution for this. Okay, so given. So this time you're going to write a CSTR. So not a plug flow reactor. Levenspiel already give you working equations for the plug flow reactor. So it's better that we work on something different. So this is our scheme for this CSTR. Oh, lang. We'll use the different color here. Okay. So if we're going to label, this would still be FA1. This would still be VA1. Since this is the recycled path class, I'd like to label this as V sub R. And I like to label this as FA2. This would be XA2, or rather, I will just label this as concentration. Then you will have here V2 also, small V2. You will have here CA1. You will have here as well CA2 because that's the same concentration. But you will have here V3. Okay. We have this node here. Have this node here. We have here FAO. And you have here VO. And we'll have here CAO. We'll label we'll place the values later. And we'll have here FA3. So we have molar feed rates, we have concentrations, and we have volumetric flow rates already complete. By the way, this is also CA2. Okay, that's also CA2. What is given in the problem is says that you have this particular reaction. And this is the rate law. So your set units for this is pound mole per cubic feet per hour. And what else? Your VO is 100 cubic feet per hour. I'll just transfer it here so I can write it. You have VO is 100 cubic feet per hour. Concentration is 1 pound mole per cubic feet. I'll write it here. The product removed contains 50 pound mole per hour of unreacted A. So it's the unreacted rate A in this case. So this is your product. This is the main product. FA3 is 50 pound mole per hour. So the term that was used is the product removed. So it's not this one, but rather this is already the final product, because your FA2 is not yet your final product because a part of it is returned. A part of the unreacted most of A is returned back into your system together with the original feed that is to be processed. So the product removed contains 50 pound moles per hour of unreacted A, and that's a steady state condition. Hold up time, so this has something to do with tau. 15 minutes. So you're required. Place here. You're required to determine the reactor volume. That's V. And the recycle rate. So in cubic feet per hour. So the recycle rate is being asked based on our drawing. Our representation is this. Our recycle rate, because it's the one that is stipulating what should be the unit. So the unit, cubic feet per hour, tells you that the recycle rate that is being asked, by the problem, is the volume that is being recycled. So this is P sub 3. And it should be in cubic feet per hour. Okay. So this is our given. If you have your problem, you can check on the given before we start with the solution. Have any question here? Let's say that's node 1. And this is node 2. No more question? Now, by the way, this one, the 50 pound mole per hour of the final product removed, which is the unreacted part of A, can also be expressed in terms of the equivalent expression that we have when we start with ideal reactors. Molar feed rate is equal to concentration times volumetric flow rate. So we can have it written as that then it tells us that the product of these two is 50 pound mole per hour. Okay? Now we go to our solution. So one way of starting this problem is you do material balance. You do material balance based on the nodes that I have identified. So this is your node 1 and this is your node 2. Can you please take a picture? That way it would be easy. We don't need to go back to this illustration. Okay. So we know that if we are asked for the volume of the reactor, that volume of the reactor divided by the V1 should be the tau. Okay, remember, your V1 is this, or VA1. V1, because anyway, it's processing. We're basing everything on A, so we'll just have it V1. So the volume of this particular reactor is equal to, or rather the tau of this particular reactor 2 is equal to its volume divided by the volumetric flow rate that entered it. And that's the V1, the sum already of the VR and the VO, the original 100 cubic feet per hour that is introduced into your CSTR. So from here, this would be your guide equation. You have an equation already that will solve for the volume of your reactor. So that would be V1 tau. So for now, we can solve for it because so far we only know the tau. We don't know V sub 1, the small V sub 1. So that would be our equation 1. Now, if you do material balance on node 1, so we will base our material balance based on the molar flow rate. So initially we have FAO and we add to it the FAR from the recycle stream, and that would be equal to FA1. FAO plus FAR is equal to FA1. Okay, based on node 1. So we can now convert this expression in terms of what we have written here on the given. That it could be expressed in terms of the product of concentration and volumetric flow rate. So we can do that. So this would be written as V, small VO, CAO. And this would be your VR times your concentration 2. It's labeled anyhow, so you can see that in your screenshot. And this is equal to small V1, CA1. Okay. Now we can solve for CA2. Your CA2 is equal to FA3 divided by V3. Now we know that V3 based on your illustration is equal to VO. Okay, on your screenshot, you can see that this V3 should be equal to this VO. If you cut here, your V3 is equal to VO. Okay? So that's it. And your CA2 here is equal to, or it could be a function of FA3 and V3. So you can see this one. FA3, V3, because if you cross multiply, your FA3 will be the product of CA2 and V3. So you know these two, so you can substitute the value. So your FA3 is 50 pound moles per hour, and your V3 is 100 cubic feet per hour. So you cancel this, you get a CA2 which is 0.5 pound mole per cubic feet. Okay, now by the way, this is our working equation based on node 1. We can solve anything for now. We'll have that as equation 2. And we can make material balance on the reactor itself. And that would be Ca1. Okay, the concentration of the stream that is being processed by your MFR is equal to the unreacted part plus the part that was processed by your, or due to the processing of your reaction. Okay, this one. Okay, initial concentration that enters your MFR is equal to the final concentration plus the concentration due to reaction, or the concentration that was converted due to reaction. A portion of A that was converted due to the reaction. So we can have Ca2 now. This Ca2 substituted here. So you have 0.5 plus this rate is 2Ca, right? 2Ca tau. So I can write this again as 0.5 plus 2. And the Ca, since we're talking about the MFR, is specifically Ca2. So we multiply this also by 0.5. And we multiply it by the tau. Now, our tau is in minutes. Our volumetric flow rates and molar feed rates are in hours, so we convert it to hours. So we divide by 60. So that will uniform, I will have a uniform unit for time, which is in hours. So in this process, you have now Ca1. 0.5 plus 2 times 0.5 times 15 over 60. That should give you an answer of 0.75 pound mole per cubic feet for Ca1. Okay, so we know Ca1, we know already Ca2. The Ca1 and Ca2 here, CaO is known, so that will help us find the VR. So, but your V sub O based on node 1 is equal to, or that would be the V1. Node 1, you could refer to your illustration. V1 is equal to VO plus VR. So the purpose of having this equation, which is 100, so your VR is equal to 100 minus V1. This is equation 3 already. So the purpose of having this is because even if you substitute already Ca1 and Ca2 on the first equation, Ca1, Ca2, we know CaO, but your unknowns will be VR and V1. You only know VO. So for you to be able to find VR from equation 2, you need to have an expression relating V1 in terms of VR. So we just did that. VR is 100 minus V1. So you can go back to equation 2, substitute values, and 3 to equation 2 for you to be able to find the VR. So VOCAO, so we know it's 100 and CaO is 1. Let me check 1. So 101. So this is from equation 2 is equal to VRCA2, Ca2 being 0.5 plus, so C V1, or rather equal to V1 Ca1. So this should be plus. Your V1 is, or we can have V1 is 100 minus VR. So that we can right away determine VR. And we multiply it with CA1, which is 0.75. You'll be able to solve for VR. Can you please solve for VR?
Negative 20.
Negative. Wait lang. Wait lang ha. POCAO B plus BRCA2 is B1. Oh, this should be plus. Sorry. B plus. BR, please.
$100 miss.
Okay. Diri siya na nagsala. Okay, minus butang ko. It should be plus. Thank you, Nika. So you have 100 cubic feet per hour. So we determine first the letter B. So this is already letter B. For letter A, we need to determine first the V1. So V1 is equal to 100 from here plus 100. So that would be 200 cubic feet per hour. So based on equation 1, the original equation we wrote so we can determine the volume. It should be V1 tau. So 200, B is equal to 200 times the tau, which is 15 over 60. We have a volume in cubic feet equal to 50. Okay? This is from this one is from 3. You have any questions so far to the solution? Here, we wrote first the working equation for the requirement, the first requirement, which is the volume of our MFR. And since we know that from this particular equation, we need the V1, we can only have the V1, we will only know the V1 if we get to know the recycle stream, the volume that is recycled, because based on nodal analysis, your V1 is dependent on VR. So that's the purpose why you made material balance on node 1. So your material balance is based on molar feed rates, flow rates rather, and it was converted to products of concentration and volumetric flow rate. So we don't have all the information here, so we found what we can found based on the given. So we know that the final concentration of the unreacted moles of a living as a product from your CSTR is this one, 50 divided by 100. So we need to make a balance on the MFR. That way we can find the CA1. These two concentrations you need here. Okay, because the only concentration originally given is the initial concentration. So you need these two. So you now know that. But still, you're still left with the problem of the V1 and the VR. So when you do nodal analysis again, based on volumetric flow rates on node 1, so this is from, or this is based on node 1. So this equation is based on node 1. Your V1 is VO plus VR. So we get this expression that way. We can express our V1 in equation 2 in terms of VR and solve for VR first. When you know VR, you can now go back to equation 3 and solve for V1 and pabalik siya and knowing V1, you can go back to equation 1 to solve for the volume of your CSTR. Okay, actually, there's no specific procedure as to what should be the steps that you need to take. But we always start with the working equation if available for the unknown that is being asked. And from there, you know that you will have still unknowns. You just find for the working equation that will find those unknowns. But in the case of the recycle reactor, so take note that you will always do guide nodal analysis on particular streams that meet, and then your reactor itself. So your material balance could be based on a particular node, or it should be based on a particular node and based on your reactor that is given. Okay? So that ends our lecture on reactors, design of single reactors, multiple reactors, and recycle reactors. The rest would be, you need to do preparation on your CLE. So with the remaining time that we have, I will now make an announcement in Canvas as to the specifics of your CLE. That way you will be guided. There will be 2 topics that will be delivered in the form of reporting by the groupings that I will also make. So I will make it after this class now. That is if you don't have any question. I'll stop sharing. Do you still have concerns? Why naman? Sige. So with the remaining time, I still have time, around 23 minutes. I'll work on the announcement on Canvas. Just check it. You just checked it after 5 to 10 minutes. Okay? For the rest, no more questions.